Hi, my name is Mackenzie Poncel, and this is my Physics 2211 Lab 4, Motion of an Oscillating Spring. In this lab, we will create a computational model of an object attached to an oscillating spring. We will use Python to model the spring and the ball's motion. We will then iteratively calculate the energy changes in the different types of energy found in our system. We will compare the computational model to the experimental values determined by the motion tracking software Tracker. The system is defined as the Earth, the spring, and the ball. We know the ball's mass and the stretched spring length L. We use two fundamental principles, Newton's second law, which you can see on the right how it's written in the code, and also the energy principle. We also use three different energy calculations, kinetic energy, spring potential energy, and gravitational potential energy. You can see in the code on the right those last four calculations. We were given a video to upload into the motion tracking software Tracker. The fixed attachment point is our origin, 0, 0, and when the video starts, you can see that the graph on the right is created. It is the x position versus time. You can see as the graph moves along the points that are plotted. Once the video starts again, you can see that a different graph is created, the y position versus time. The graphs look slightly different. The motion through the graph is still the same, but the starting points are very different. There are some characteristics of the spring that we still need to calculate. The spring constant K is calculated as 4 pi squared times the mass divided by the period T squared. We find that K is equal to 6.88 newtons per meter. We also need to find the relaxed spring length, L naught. We know that the magnitude of the force of gravity is equal to the magnitude of the spring, and from there we can calculate that L naught is equal to the magnitude of L minus mg over K. We find that this value is 0.127 meters. We also need to find the period. This is 3t, which we find to be 4.557, and to find t, we divide by 3 and get 1.519. You can see how these values are inserted into the code here on the right. This is the GlowScript code that will be used to find the computational model. We start with some initial conditions such as the ball's mass, ball position, and ball velocity. These can be found by the tracker data. We then have the constants such as gravitational constant, spring constant, and other characteristics of the spring, as well as the calculations for the energies. We use this while loop to calculate the change in energy. We have the F net, which we apply to the momentum principle to update the ball's position and velocity. We then have this calculation chain here of the energies, and we calculate them as they change with respect to time. When we run the program, we have to include a CSV file, which is all the X and Y data points from Tracker. You can see the change in energy versus time graph. Delta E, the orange line, is 0. The code also produces the X position versus time and the Y position versus time graphs and the comparison between the experimental and the computational model. As mentioned before, the X position and the Y position versus time graphs of the experimental data are going to look differently. However, the X position versus time and the Y position versus time from the model is also going to look different, and it is not going to align with the experimental data perfectly. You can see that the X position versus time model and experimental graphs align closer. This is because the X position only is influenced by the velocity. The Y position is influenced by the force of the spring as well as the force of gravity. For your model, is the energy principle satisfied? Yes, the energy principle is satisfied for this system because the total change in energy, delta E, is approximately 0. Delta E is that orange line you see in the graph on the left. We know that the energy principle is satisfied and it is 0 because there are no interactions from the surroundings to our system. Different oscillation periods can be computed depending on which set of data points you look at. If you use the X position data points, the oscillation period is 1.646, and if you look at the Y, it's 1.519. In the code, we use 1.519 because this includes both the force of the spring and the force of gravity. In the X direction, this only accounts for the pendulum motion caused by the change in velocity.